Okay, so let's pick up where we just left off. We were talking about the differences between the two types of DSC instruments. Regardless of which type we use, we can get a lot of information based off how the two pans and the energy changes differ from each other. We can figure out what the melting point of our compound is. We can figure out whether there is solvent trapped in those crystals through desolvation. We can look at glass transitions, which is kind of a melting point of an amorphic solid. We can look at heats of transitions, the amount of heat absorbed or released when compounds go from one state to another. We can figure out, is our compound pure? We can look at the transition from one polymorphism to another. We can look at whether two compounds are compatible with each other, and we can see how quickly a compound is going to decompose. So this is an example of a readout from a DSC instrument. And like I mentioned, it doesn't matter whether we use one type or another type of DSC instrument, the readout is going to be the same. And we call this readout a thermogram, okay? So on the x-axis, we're generally going to have temperature. Usually we start at low temperature and just slowly heat it up, but we can do it the opposite way around. On the y-axis, we have heat flow. And what I put in here is that as we go up on the y-axis, that means the process that is occurring is exothermic, okay? Now this is, I'm gonna walk you through this. This is not necessarily self-explanatory. And so what we're looking at, what the readout is, what the number represents, is the difference between the two pans. And so imagine this is the zero line here. And so we're heating it up, and there's no difference between the two pans. And so we have a flat line. As this line goes up, we are actually getting a readout of what's having to happen in the reference pan. And so this is telling us that we are having to put more heat into the reference pan. And so think of this as the power compensation DSC. We have to put more energy into the reference pan in order to get it to the same temperature as our sample pan. And so that means our sample must be putting energy into the pan. So the powder that we put in that pan must be putting energy into that pan, which means an exothermic process is occurring. And so this is an example of a change in specific heat. Change in specific heat, remember specific heat is how much temperature change occurs per amount of heat that we put into a sample. If an exothermic process occurs, no matter what it is, we have to put more energy into our pan in order to keep up with our exothermic process. An endothermic process means that our sample, our powder, is absorbing heat from our pan. And so in our reference pan, we don't have to put any heat into it at all. And so we put less heat into it, and so we see a decrease. That's an endothermic process. So let's just take a look at some actual thermograms here and how we can get information from them. So this is a sample where on the x-axis we are increasing the temperature, and we see that we have essentially a flat line, and then all of a sudden we see this peak. In this situation, this is a melting of a crystal, okay? So melting requires energy, right? That is an endothermic process. And so our graph is going to go down. Once it is completely melted, now we're going to jump back up and then we're going to resume right where we started. There's two important pieces of information here. The first is the melting point of our solid. It is the point at which this peak starts to go down. It is not the point at the bottom. It is where this peak or the drop starts. If we take the integral, or the area under the curve, within this little peak here, that is going to tell us the heat of fusion, or the heat of melting, depending on whether you're going from solid to a liquid or liquid to a solid. It's going to tell us the amount of heat required to melt that amount of solid that we put in that dish. This is a similar looking thermogram, but notice that there are two peaks. And not only is there two drops here, but there's a peak that goes up in between them. So in this situation, we have two polymorphisms. So in this case, what we do is we're going along, we're heating it up, and then all of a sudden, the first polymorphism starts to melt. It melts, and after it melts, though, it reforms a different polymorphism. And so the first melting event is endothermic, but when it reforms a different polymorphism, that is actually endothermic, so we see a peak up. And then the second polymorphism starts to melt, and so we see a second peak down. In this one, we're seeing a pseudo-polymorphism. So remember, a pseudo-polymorphism is when we have a solvent that is trapped in our crystal. In this situation, we have water that is trapped in our crystal. So as we heat it up, we see a peak, and then we see another peak. The first one is a process of getting the water out of the crystal. The second one is the crystal melting. And so you might be thinking, how do I know that this is a dehydration event followed by a melting event rather than two polymorphisms like we saw on the previous slide? There's two clues here, but it's never a cut and dry conclusion. It's always your best guess based on your experiences. So number one, notice that there's no exothermic peak, transition peak between the two peaks that go down. Also, dehydration starts kind of gradually before becoming sharp. melting peaks almost always are sharp. If you see something that's gradual, that's a clue that you're probably dealing with a dehydration peak. In this one, we are looking at the melting of an amorphic solid. And I give it the air quotes because melting is going from solid to liquid, but we said an amorphic solid is technically really a liquid to begin with. And so in this situation, we're really just going from a high viscosity liquid to a low viscosity liquid. So in this situation, we have a very, very, very broad peak. That's our dehydration event. And then we have this very awkward looking thing. Now, there are a number of things this could be. This could be an ugly melting point. It could be a second dehydration or desolvation event. But in this situation, it is a glass transition. There's no way I would ever give you a thermogram and ask you to recognize that what you're looking at is a glass transition. But if you ever do work with DSC traces, keep in mind that something like this could simply be a glass transition and not something more complicated than that. I mentioned that another thing we can use DSC for is to determine the purity of a compound. Now, something you may remember from organic chemistry, if you took organic chemistry, is that the melting point is partially determined by its purity. And the more pure a compound is, the higher its melting point is going to be. Always, always, always. If something is impure, its melting point will be lower. No exceptions. So in this case, if we look at the melting point, remember the melting point is where we start to see that drop. The 99.97 pure sample has the highest melting point, the 99.5 is the second highest, and then the 99% is the lowest. I remember when I took organic chemistry, every time we made something, we had to look up the theoretical or the literature melting point of a compound, and then we had to report the melting point of our compound. Usually, our melting point would be lower than the literature version because we were organic chemistry students. We were not professionals, and so our compound would be lower. So our melting point would be lower. If we ever got a melting point that was higher than the literature value, we had to prove or explain why our compound was actually more pure than what the professionals got. And so every time you did a melting point, if you measured it and it came out higher, you kind of questioned yourself and you wanted to go back and redo it again because probably what happened is you did the melting point determination incorrectly. But here we can see very clearly that not only do the melting points get lower with a lower purity, but the peak shape changes also. The highest purity is very sharp and the lowest purity is a broader drop. The last thing I want to talk about is not DSC. This is one more analysis technique that I briefly want to discuss. That is thermogravimetric analysis. This one is very simple to understand. In this situation, we have two pans again. We have our reference pan and our sample pan. We put our sample over here. We put them in the same oven. We heat the oven up, and we measure the mass of the two. If the mass changes, that means something is happening to our sample, right? Things don't change in mass simply because you heat them up. And so if the mass goes down, there are a few things that can be a indicator of. Number one, it could be a matter of showing you that there is solvent trapped in your crystal. So as you heat it, that solvent evaporates. As the solvent evaporates, your mass is going to go down. It could be a matter of decomposition. Your compound could be falling apart and making new compounds, one of which may be a gas. And if it's a gas, it's going to leave the sample and your mass is going to go down. It is possible for the mass to go up, okay? Think of a situation where something reacts with oxygen. Something likes to burn at a high temperature. And so if it reacts with oxygen at a high temperature, you're going to take the mass that you started with, add some oxygen from the atmosphere, and your mass will go up. We can also use a similar technique to measure the compatibility of two compounds. So in this situation, we don't even have to raise the temperature in our little instrument. We can just mix two compounds and watch the mass. If the mass changes, that means those two compounds must be reacting with each other in some way or another. So that means we don't want to put those two things together in a pill, right? Sometimes we make a combination pill, but we need to make sure that those compounds are compatible with each other so they don't react with each other, potentially lose their potency, potentially lose their efficacy, or maybe even worse, make a toxic product from that reaction. So I hope you found that interesting. Think about these things. Make sure you can understand the difference between the DSC instruments. If you have questions, let me know.